Welcome to this explainer. When we look at the ocean, it's easy to just see a giant static pool of water. But today, we're diving into Chapter 10 to see what's really going on. We're going to uncover the massive, invisible forces shaping our oceans, treating them exactly like what they are, a living, breathing machine that literally regulates our entire planet.
Here's our quick roadmap for today. We're going to cover the ocean's two main engines, wind and the Ekman spiral, gyres and geostrophic flow, upwelling and downwelling, how to navigate these surface currents, and finally, the massive global conveyor belt.
All right, let's jump right into part one, the ocean's two engines.
So the absolutely crucial thing to grasp right off the bat is that ocean movement isn't just random. It's powered by two completely distinct, non-stop engines. First up, we've got the wind engine driving the top layer. Then right below it, there's the density engine, powering the deep ocean. Now, because water is 1,000 times denser than air, it carries incredible momentum. The wind gets those surface currents whipping along, but deep down we have what's called thermohaline circulation. This is driven by tiny, minute changes in temperature and salinity, creating this incredibly slow, powerful movement right across the seafloor.
Okay, moving on to part two, wind and the Ekman spiral.
So how exactly does the wind fire up that first engine? Well, when wind blows over the open ocean, it doesn't just push the water straight ahead. Because our Earth is spinning, we get the Coriolis effect. This actually deflects that very top layer of water at a 45-degree angle to the wind, specifically to the right if you're in the northern hemisphere. Now, because of friction, that top layer physically drags the layer right below it, deflecting it even further. As you go deeper, the water moves a bit slower, but that angle just keeps twisting and twisting. It forms this absolutely mesmerizing corkscrew pattern that we call the Ekman spiral.
And the net result of all that twisting? It's actually really wild. By the time you get down to about 150 meters deep, the wind isn't directly affecting the water anymore. But if you take the average movement of that entire 150-meter column of water, the net transport, which is known as Ekman transport, is shoved a full 90 degrees away from the direction the wind is blowing. A perfect right angle.
Which brings us to part three, gyres and geostrophic flow.
That 90-degree push we just looked at, that's the exact mechanism that spins up these massive ocean whirlpools called gyres. Imagine the trade winds and westerlies blowing across the sea. Ekman transport takes that water and shoves it inward toward the center of the ocean basin. And I mean, it physically piles the water up into a literal mound. Of course, gravity wants to pull that water right back down the slope, but the Earth's rotation, the Coriolis effect, pushes it right back in. When those two forces perfectly balance out, the water ends up flowing smoothly in a giant circle, and that right there is geostrophic flow. You can actually see this happening in real life over in the Sargasso Sea in the North Atlantic. Because the Earth is spinning, this massive mound gets shoved over to the western side of the basin, and it can actually reach up to 2 meters high. Think about that. There is literally a hill of water sitting out in the middle of the ocean, taller than most of us, and giant surface currents like the Gulf Stream are just constantly flowing right around it.
Let's dive into part four, upwelling and downwelling.
Now, water obviously doesn't just travel in flat horizontal circles. It moves vertically too. When the wind blows surface water away from a coastline, a process we call divergence, freezing cold, deep water has to rush up to take its place. We call this upwelling. On the flip side, if the wind is pushing surface water toward the coast, creating a convergence, well, that water has nowhere to go but down. It forces oxygen-rich surface water deep into the ocean, which is our downwelling. So why should we care about water moving up and down? Well, this vertical movement is an absolute game changer for marine life. Upwelling basically acts like a giant ocean fertilizer. It drags cold, super nutrient-rich water up from the dark, murky depths right into the sunlit photic zone. And that sudden burst of nutrients, it fuels massive biologically rich food webs, like the insanely productive fisheries right off the Peruvian coast.
Next up is part five, navigating surface currents.
Let's zoom out for a second and take a global tour to see how all this local physics actually draws the map of our oceans. Looking at the whole planet, we can trace these immense gyres flowing clockwise up in the northern hemisphere and counterclockwise down in the southern hemisphere. But check out the outliers. You've got the massive Antarctic circumpolar current just tearing around the globe, completely unimpeded by land. And over in the Indian Ocean, seasonal monsoons are so strong they actually force the surface currents to completely reverse direction twice a year. These flows are so steady and predictable that oceanographers literally call them rivers without banks. But if you look closely, you'll notice these gyres are actually pretty lopsided.
Because of the Earth's rotation, water naturally piles up on the western edges of the ocean basins. This causes a really cool phenomenon called western intensification. Basically, currents on the western side, like the Gulf Stream, become incredibly fast, deep, and narrow. Meanwhile, eastern boundary currents, like the Canary Current off the coast of Africa, are broad, shallow, and frankly, a bit sluggish.
Zooming into the North Atlantic, this western intensification is super obvious. The Gulf Stream is just incredibly energetic. As this fast-moving water crashes into slower water, it starts to meander and actually pinches off these massive spinning rings of water called eddies. You get warm water eddies spinning off into freezing northern waters and cold eddies spinning right down into the warm Sargasso Sea. They act like these massive, isolated, traveling aquariums, moving marine life completely outside of their normal habitats. They're literally so large they can even change the strength of a hurricane passing right over them. It's wild.
Over in the Pacific, we've got the super productive Peru Current running along South America, which is totally driven by that coastal upwelling we just talked about. But enter El Niño. During El Niño years, the typical high and low atmospheric pressure systems in the South Pacific totally shift. This completely scrambles the trade winds, which then stalls that crucial Peru upwelling. The ripple effects for the global climate are immense, and it effectively shuts down one of the most productive fishing grounds on the entire planet. Finally, let's wrap things up with Part 6, the global conveyor belt.
All right, we're leaving the wind-driven surface behind entirely and sinking into the ocean's second major engine. Down here in the pitch black, thermohaline circulation runs the show. Thermo meaning temperature, and haline meaning salinity. This deep circulation kicks off at the extreme poles, near Greenland and Antarctica. The surface water there gets freezing cold, and as sea ice forms, it spits out the excess salt. This makes the surrounding water insanely cold, salty, and dense. So it simply plummets straight to the ocean floor, forming these deep water masses that begin to creep horizontally across the globe. Now, keep in mind, there is absolutely zero wind down here to push things along. Because this incredibly dense water is just creeping along the bottom of the basins, it takes a staggering 1,000 years for a single parcel of water to complete one full cycle. Seriously, let that sink in. Water plummeting to the ocean floor today won't see the sunshine again until the year 3024 is...
That epic 1,000-year journey? That's what we call the global conveyor belt. It's a massive, slow-motion loop that connects every single ocean basin on Earth. It drags freezing, dense water along the seafloor and eventually cycles it back up to the surface as warm, shallow currents. It's essentially the Earth's ultimate planetary thermostat, pumping vital heat around our entire globe to keep everything in balance.
So, as we wrap up today's explainer, I want to leave you with a pretty crucial question. If this massive, interconnected machine dictates our planetary temperatures and weather systems through a super delicate balance of heat, salt, and density, what happens to our world if the conveyor belt begins to stall? What actually happens if our warming poles stop producing that dense sinking water? It's a totally fascinating and honestly, a deeply important question to think about. Thanks so much for exploring the engines of the deep with me today. Keep exploring.